Hi, I'm John Brown, a graduate student in the astronomy department at The Ohio State University. In this coffee brief, I'll be presenting recent results from my paper with Kevin Croxall and Rick Pogge titled Direct Method Gas Phase Oxygen Abundances of 4 Lyman break analogs. Lyman break galaxies are starburst galaxies at redshifts greater than 2. These galaxies dominate star formation in the early universe and are thought to be the progenitors of the bright elliptical galaxies we see today, making them particularly relevant for studies of galaxy formation and galaxy evolution. However, due to their high redshifts, it is often difficult to study these galaxies in any great detail. Over the past decade, the combined usage of the Galaxy Evolution Explorer and the Sloan Digital Sky Survey have allowed for the identification of a new class of galaxies coined Lyman break analogs. These analogs are thought to mimic the compact starburst nature of Lyman break galaxies, but are located at much lower redshifts, typically z of 0.2 rather than z of 2. Galaxies in the local universe have been shown to define a tight relation between stellar mass and gas phase oxygen abundance. This relation has been termed the mass-metallicity relation and spans over 3 orders of magnitude in stellar mass and over 2 orders of magnitude in oxygen abundance. The energy level spacing of doubly ionized oxygen is such that the ratio of the auroral to nebular emission lines is sensitive to the temperature of the gas. Thus, if we can measure this ratio, we can determine the temperature and oxygen abundance of the nebula. However, the auroral line is intrinsically faint and thus difficult to measure. As a result, oxygen abundances of very faint objects are often estimated using ratios of bright, easily measured emission lines that correlate with oxygen abundance. This is known as the empirical strongline method and requires a local sample of ionized regions with directly measured oxygen abundances in order to calibrate how the bright emission line ratios change as a function of oxygen abundance. If the ionization conditions of faint objects like Lyman break galaxies and Lyman break analogs are significantly different from the local objects used to calibrate the empirical relations, their strongline abundance estimates could differ significantly from their true oxygen abundance. We performed spectroscopic observations of 4 Lyman break analogs using the MODS instrument on the LBT in order to test whether or not the locally calibrated empirical strongline methods yield accurate abundance estimates when applied to these exotic objects. This figure shows an example of one of our spectra obtained with MODS compared to an SDSS spectra of the same object. Note the stronger detection of the auroral oxygen line in the MODS spectra compared to the SDSS spectra. In all 4 objects, we are able to measure the auroral line of doubly ionized oxygen. We use this to measure the electron temperatures and then derive ionic abundances, including oxygen abundance, for each target. With the direct method oxygen abundances in hand, we plot where the Lyman break analogs fall on the mass-metallicity relation for various oxygen abundance diagnostics. The cyan dots here show our direct method oxygen abundance, while the thick black line shows the direct method oxygen abundance of stacked SDSS spectra from Andrews and Martini 2013. It is immediately clear that the Lyman break analogs fall well below the mass-metallicity relation defined by local galaxies. Given the scatter in empirical relations of about 0.3 dex, we find that the N2 method estimates for these 4 objects are generally consistent with our direct method oxygen abundances. Lastly, we investigate where the Lyman break analogs lie on the fundamental metallicity relation. As shown in this plot, accounting for their high star formation rates greatly reduces the degree to which they are offset from SDSS galaxies, suggesting that the Lyman break analogs follow the fundamental metallicity relation. For additional details and discussion, be sure to take a look at our recent paper posted on the archive. Thanks for watching.